Hey, so finishing this topic, looking at now the washer method. So in the last section, we looked at a region that was bounded by a curve and a straight flat line. That straight flat line could have been another function, could have been an extra y-axis. In the washer method, look at a region bounded by two curves that are not horizontal or vertical lines. Alright? Now, the reason we call it the washer method is think about nuts, bolts. When you put them together, usually you use a washer with the nut and the bolt when you screw it in, so the washer can be up against a flat object and kind of give you more security when you're screwing it. But the washer has a hole cut out in the middle. Alright, so from the center of the hole, there's a bigger radius that goes to the outside of the washer, and the smaller radius that goes to the inside of the hole of the washer. So it's still pi r squared. As you can see, pi, r, and squared. But now there's a big R, the big radius, and a little r, a little radius. So you know how top minus bottom, how you find the length of a rectangle or the height of a rectangle? So that's how you find the height of a representative rectangle in an area. Imagine there was a large object taken from the top radius, the big one, and spun around to get you an area, so something like that. And imagine this is a three-dimensional object, so it was back, kind of, this on this side, or like that. There you go. That's better. But then there's also a smaller radius that's also revolved, and the smaller radius cuts out a part of it. So it creates kind of a hole in the middle of the shape, okay? That smaller volume bounded by the red is removed, kind of that green shape is cored, and the core is removed, so now it's open in the middle. So the big overall green volume minus the smaller red volume from inside. And of course you can do this horizontally also. You still have pi r squared and then little r squared, but now it's in terms of y and dy. So let's take a look how this works, okay? So we have a volume formed by revolving the region bounded by the graph of f of x and y equals x squared about the x-axis. So we have from 0 to 1 a square root function. I can do better. Okay. So that's f of x. And then x squared that's y. So we have our region right in here. And we're going to revolve that region about the x-axis. So down here, we have our AOR, axis of revolution. And in this axis, there's a big R of x from the axis to the far side of the area. And we have little r of x from the axis of revolution to the near side of the region. So to set the integral, of course, pi going from 0 to 1 of big R squared minus little r squared. So big R is root x squared minus little r. Little r is x squared dx. Then we go about kind of simplifying down like we usually do. So root x squared is x. X squared is x to the fourth dx. So let's anti-differentiate. We get 1/2 x squared minus 1/5 x to the fifth. This is going from 0 to 1. So thankfully, one of our bounds is 0. So don't really have to worry about that one. So just 1/2 1 squared minus 1/5 1 to the fifth. So that is 1/2 minus 1/5. And that would be 5/10 minus 2/10. So 3 pi over 10. Can really appreciate as a human accomplishment. That's what the syllabus says. But appreciate the fundamental theorem of calculus, how it really does all the work for us. We just got to tell it what to do. What's the big R, what's the little r, and then it takes care of the rest. Integrating with respect to y. This is always kind of tricky because we're very used to things being in terms of x. So now in terms of y. So find the volume of the solid formed by revolving the region bounded by the graphs of all of that. So first things first. I want black, okay. First things first, y equals x squared plus 1. That is x equals root y minus 1. Okay, to kind of get that down to begin with. So now we're going to graph this. And to make it easy, we'll graph it in terms of x, so keep the paper vertical like it is. So you have x squared plus 1, so 1 times 1, upon of 1, upon of 1. Can just draw that parabola there. We have y equals 0, x equals 0, and x equals 1. So the x and y axes, and then x equals 1. So kind of here, here, and there. And that's our region that we're going to revolve about the y-axis. Now in this region, part of the region is flush against the y-axis. So this block right here, that's flush right up against the y-axis. We can do disk method for that. So there's just the big R of y. So when you do volume, we have that one, pi from 0 to 1, because we're going 0 to 1 to the y-axis, of big R of y, which is the length of big R of y is 1, so 1 squared dy. And then we need the volume for the other part, the 1 to 2. So that will require washer method. So we're going to be adding pi from 1 to 2. We need a big R and a little r. Big R goes from the axis of revolution to the far side of your region. So that would be big R phi. Then little r phi goes from the axis of revolution to the near side of your region. So big R, again, is going to be that 1 squared, just the distance from the axis to the far side. From the vertical y-axis to the vertical line x is 1 is 1 unit. Little r, which you subtract, is going to be root y minus 1 dy. So we have big R and we have little r. So now to calculate all of that, pi from 0 to 1 of 1 dy, we're going to add on the other area from 1 to 2. Let's see, 1 squared is 1. Root y minus 1 squared is y minus 1. Going to be subtracting all that, so a negative y plus 2. So 2 minus y dy. And then you can solve that from there. Check your work with my complete notes online. But then I want to look at example A. Maybe B, maybe C, but example A for sure. Think about the above example, but what was the integration setup? The setup only, so just the setup, okay? Write, but do not evaluate the integral. If we evolved with a line x equals -1, okay? So let's get a drawing of how that could look. So we have xy axis, we have a region, but now we're evolving about the line x equals -1. Alright, x equals -1. So we still have two integrals, okay? One of them is still that region from 0 to 1. So right there. Big R gonna be right there. Little r, again, from the axis of revolution to the near side of your region. Now these are all horizontal lines, or sorry, these are all vertical lines, very easy to find their lengths. Let's bring this down. So our volume would equal pi from 0 to 1. Big R would be from -1 to 1, so 2. So 2 squared. Little r would be from -1 to 0. So 1 squared. It really helps when you're doing these to draw pictures, okay? Now let's do our other integral. From 1 to 2. So there's big R from the axis of revolution to the far side of the region, then little r from the axis of revolution to the near side. Now to the far side, -1 to that other vertical line at x equals 1. So again, big R going to be 2. Little r is going to be from -1 to the root y minus 1. So there's 1 unit. There's 1 from -1 to 0. And then from 0 to region. So plus root y plus 1. That's our little r. That's going to be squared dy. For example B, I'll about the line y equals -2. Okay, let's kind of draw this picture. So xy axis gives you a region, but now we're revolving about the line y equals -2. So y equals -2. Now luckily, this will only be one integral, because from 0 to 1, you just have the curve on the top. So we only have one integral, one big radius, one little. So your big r of x and your little r of x. Zoom out a little, there we go. So to get your volume, that's pi from 0 to 1 of big R of x. So big R of x, that distance, from -2 to 0, that's going to be 2 units. Then we're adding on from 0 to the curve. That is 1 plus x squared and that's your big radius. Let me check, make sure the function x was 1, okay. And then you're subtracting the small radius. Small radius from -2 to 0, that's 2 units. Can you get a bigger set of brackets over this? For dx. So big radius, little radius, squaring them both and then subtracting them. So take a look, finish example 4, take a look at example C, check out work with my completed notes online.